Hello, everybody. It is my great pleasure to introduce Dr. Shuo Qin, our speaker for today. Dr. Shuo currently is sharing postdoctoral instructor at the Beijing Institute of Mathematical Sciences and Applications. Shuo recently completed his PhD in mathematics at New York University under the supervision of Professor Pierre Terres, with a thesis focused on reinforced random walks and interacting air models. His research lies at the intersection of probability theory and statistical physics, with a particular interest in self-interacting random processes and random walks in dynamically changing environment. His work has already been recognized in top journals, including a forthcoming article in the Annals of Probability. Shuo has held visiting positions at Sorbonne University and has presented his work at numerous international events, including the NYU Shanghai, Kyoto, Waseda Young Probabilists meeting and seminars at institutions like Shanghai and East China Normal University. Please join me in welcoming Dr. Shuo, and which gives us a talk with title about the elephant random walk and one half. Please, Dr. Shuo, we can start.
Okay, thank Professor Agish for the kind introduction. So, can you hear me now?
Yes,
Yeah.
yes.
Okay. So, my name is Shuo Qin. So, now I'm a postdoc at the Beijing Institute of Mathematical Sciences and Applications, BIMSA. So, I'm very happy to be invited to give the talk at this uh, applied mathematics webinar. So today I'm going to talk about the elephant random walks and trying to find the an important constant one half hidden in this model. So let's start with a question. Okay, so I use this figure to show you the definition of elephant random walk. So the two-dimensional elephant random walk is defined as follows. So the first step, the elephant choose. Okay, so let's assume that the first step is to the right, and subsequently, at each time step, the elephant records one previous step uniformly at random. So, for example, in this figure, the elephant record the step in rate from the 11 steps, so the previous 11 steps uniformly at random. Then with probability P, he repeat this remembered step. Otherwise, he choose a step from the remaining directions, from the remaining three directions. So each has probability 1 minus P divided by 3. Yeah. So then he repeat this procedure. This is called a two-dimensional elephant walk. So is
Please,
the definition clear?
please, can you repeat this step? Because it is not clear for me. How?
Yeah. So the first step, let's assume that the first step is to your right.
Okay.
Okay. Then at any time step n, so for example, in this figure, now it's at time n equals 11. So for the next step, the elephant first choose one of the previous steps. So it has made 11 steps, right? 1, 2, 3, 4. And it has made 11 steps. He just pick one steps from the past, uniformly at random. So for example, he choose this step in red.
Okay.
Then with probability P, he repeat this step. Otherwise, he choose one of the three remaining directions to move.
Okay. Thank you.
Yeah. So the natural question is whether this work is recurrent or transient. So the uh, and we are interested in this case the two-dimensional case and also the d-dimensional case. Indeed, in the d-dimensional case can be defined similarly. So the elephant choose one of the previous steps, uniform and random, and with probability p, he repeat this step. Otherwise, he choose one of the remaining d minus one directions to move. Okay. So before we result, uh, let me introduce the terminology. So for because two-dimensional elephant and multi-dimensional elephant are define what is recurrent, being recurrent and being transient, right? So we say this elephant network is recurrent if every vertex in this lattice is weighted.
Sorry.
Currently, being transient is saying that this work.
There is some problem of connection,
Yes, yes,
right?
yes.
Ah,
Okay, okay. We have to wait him.
Sorry. It seems that the network is unstable. So where shall we start? So, uh, let me introduce the definition of recurrence and transience for elephant networks. We say it's recurrent if every site is visited infinitely often, almost surely. It's transient if this work goes to infinity, almost surely. Okay. So, uh, Professor Bourtois made a conjecture that in dimension 3 and above, this work is transient. And in dimension 2, he thought this was a very challenging problem because the failure of Markovian property. And also, even in some classical random walk model, dimension 2 is usually the critical dimension. So it has been proved
excuse
that sorry?
can I ask just a question on the conjecture by Bertoin?
Yes, yes.
For the case larger than 3,
Yeah.
the walk is transient, whatever the value of the parameter p in this conjecture.
Yeah, for any parameter p, indeed.
For any p, okay, okay, thank you.
Yes, for any p, yes. And in dimension 1, it has been proved that the work is recurrent for p less than or equal to 3/4, and it's transient for p greater than 3/4. So you can imagine that for p equals 1, it's somehow you are doing a polyar model. We know that the ratio of the red bombs and the blue bombs convert to some positive limit. And this shows that essentially this shows that the work is transient for p equals 1. Yeah. So our result is the first result is uh, confirming Boltzmann's conjecture that is in dimension 3 and above, this work is transient. We also shows that there is a phase transition at dimension 2. So essentially, the work is recurrent for p less than 5/8, and is transient for p greater than or equal to 5/8. But there is a difference between in dimension 2 and dimension 1. In dimension 1, at criticality, it's recurrent. But in dimension 2, at criticality, is transient. Okay. So I'm not going to talk about going to review literature of elephant random walk today, but I have to mention that this model was introduced by two physicists, Schultz and Trimper, about 20 years ago. They introduced elephant random walk in dimension one, and it was later generalized by Becquerel and Lorrain to multi-dimensional case. So then we have seen that in dimension one and dimension two, there is a critical parameter or phase transition occurs at 3/4 and 5/8. So this shows that the critical parameter depends on dimension. The natural question is whether this critical parameter depend on the lattice. So, for example, if this elephant this work is on triangular lattice. So at each step, it has six directions to choose rather than four directions. So he randomly record step with probably P. He made a step. Otherwise, it choose one of the five remaining directions, right? So does this lattice affect this critical parameter? This will be the main question we are going to trying to solve in this talk. Okay. So we are going to generalize this elephant random walk and put it into a general framework. So if we let V, we choose possible direction V, V could be -1, E1 -1, E2 -2, the 2D possible directions for D-dimensional elephant random walk. Then we let n sub n of V be the number of steps of S in the direction V up to tan n. Then we can compute this conditional probability that given S1, S2, and until up to Sn, we compute this conditional probability that the next step is V. So the left-hand side is the definition, it's just by the definition. With probability P, we choose uh, we choose which uh, yeah. Sorry, just now the network again has. So anyway, so we can give a second formulation for the elephant random walk. If this alpha of p is non-negative, with probability alpha at each time step with probability alpha, S repeat one of its previous steps, chosen uniform at random. Otherwise, with probability 1 minus alpha, we made an independent step from the past, and this step has a uniform distribution on the 2D unit vectors, E1 minus E1, E2 minus E2, and so on. Okay, so this basically for when alpha is positive or non-negative, we have a second formulation. Then this leads us to the definition of step reinforcement works. This first step, mu is a probability measure on RD on the Euclidean space, and alpha is a constant between 0 and 1. The first step is sampled from mu. Then subsequently, with probability alpha, S repeats one of its previous steps uniformly, choose uniformly at random, and with probability 1 minus alpha, it made an independent step independent of the past sampled from mu. Okay, this is called step reinforced random walk in RD with parameter alpha and step distribution mu. Okay, the definition is simple, such an algorithm to generate this step sequence dates back to Simon. So imagine that we are writing a long book. The k plus first, the n plus first word with probability alpha is sampled from the past. So it's we choose one of the previous words, unified and random, and we repeat this word. And with probability 1 minus alpha, we generate a new, entirely new word. Then if you compute this until you repeating this procedure until the total length of this book reach some large let's say capital N, then you can compute the proportion of the words which has been used exactly once, twice, three times. Then those proportions will convert to the so-called Euro-Simon distribution. Yeah. So, but yeah, this is basically the the history of such a step sequence. So let's look at a few examples. First, well, alpha equals 0. This is just the classical random walks. It corresponds to the case. Then S is the sum of IID random variables. So each random variable is sampled from mu. So when mu, as we have seen from the second formulation of elephant random walks, when mu is uniform on E1 minus E1, ED minus ED, those 2D directions, then this becomes the D-dimensional elephant random walk. And the parameter P can be obtained by alpha through a linear transformation. And one can check that P equals the critical parameter PD, like 3/4 or 5/8, if and only if alpha equals 1/2. And when mu is a stable distribution with zero drift, this model is called the shark random swing. It was studied by Basinger. Okay. For the stable reinforcement works or the elephant works on different kind of lattice. While interesting, or still interested in the recurrence and transience problem. So let's first recall the case when alpha equals 0. Essentially it was solved by Fuchs theory. It says that in dimension 1, okay, this is a corollary of Fuchs theory. In dimension 1, if mu is centered, then we know that this classical random walk is recurrent. And in dimension 2, if mu is centered and its second moment exists, then it's still recurrent. And such a moment assumption is sharp, which means that the second moment assumption is enough, but 2 minus epsilon moment assumption is not enough. And in dimension 3 and above, if mu is centered and the second moment exists, then it's transit. Okay, so what I've seen that in the world of step reinforcement work, essentially elephant random walk plays the same role as simple random walk. If you look at the stable distribution mu, because for elephant random walk, the stable distribution mu is just like a simple random walk, like it's uniform on the 2D directions. So the natural questions: can we get the analog of Fuchs theory for step reinforcement works? Okay, this will be our objective for this talk. Before we show the main results, let me introduce some terminology. So we say S is genuinely D-dimensional if the dimension of the span of the support of mu equals D. Okay. And we say a step reinforcement walk is recurrent if there exists R such that the limit soup of Sn is less than R almost surely. And we say this step reinforcement work is transient if almost surely Sn goes to infinity. Okay, and we're going to use this notation and assumption A of S, which means that its S moment exists and is centered. Okay, so now this is our memory result. So under assumption A2, which is under the second moment assumption, is centered and the second moment exists. In dimension 1, if alpha is less than or equals to 1/2, then S is recurrent. And in any dimension, if alpha is greater than 1/2, then S is transient. So under assumption A2, the case this is so-called the super diffusive case region when alpha greater than 1/2. The super diffusive region is solved, and in dimension one is solved. For dimension 2 and higher, we need a slightly stronger assumption. It's called the a 2 plus delta's moment assumption. So it's this 2 plus delta's moment exists. So under this assumption, in dimension 2, when alpha is less than 1/2, it's recurrent. And when alpha equals 1/2, it's transient. And in higher dimension, for dimension at least 3, S is always transient. Indeed, when alpha is greater than 1/2, we only need the second moment assumption. But for alpha less than or equal to 1/2, in our paper, we impose a second moment, the 2 plus delta moment assumption. Okay. So let me add a remark here. So so indeed, this question was raised by Botwa after I solved the case for elephant work. Indeed, he even conjectured that in dimension 2, step reinforcement work is recurrent for alpha less than 1/2, even under a weaker assumption, under the second moment assumption. Yeah, but this was not proved in our paper. Okay, so let me mention a corollary. For step reinforcement work on a lattice, essentially this corollary says that. Okay, so let me introduce the terminology here. I will use script R to be the set of all states reachable for S. That is all the possible states for S. This corollary says that if this state reinforcement work is on lattice, then it will visit every site infinitely often, almost surely, if it is recurrent. So basically, this shows that the definition of recurrence and transience for step reinforcement work and elephant reinforcement work agrees for the case for the lattice case. Okay, we have shown that in dimension 1, when alpha less than or equal to 1/2, and mu satisfy the second moment assumption is recurrent. This and this corollary shows that if it's on lattice, then every site is visited infinitely often, almost surely. And in dimension 2, similarly, when alpha is less than 1/2 and mu satisfies 2 plus delta's moment assumption, then every site in this lattice is visited infinitely often. Okay, so let me let us go back to our previous question on the triangular lattice. So we have shown that the d-dimensional elephant work is a version of step reinforcement work. A similar argument shows that this elephant work on the triangular lattice is also a version of step reinforcement work. In this case, we simply take we let mu be the uniform distribution on this along these 6 directions. and we take a parameter alpha, then one can check that the reinforcement parameter p for elephant random walk is given by 5 alpha plus 1 divided by 6. And the previous results shows that there is a phase transition at alpha equals 1/2. Then this shows that for this elephant random walk on the triangular lattice, there exists a phase transition between recurrence and transience at p equals 7/12. Not even though it's still in dimension 2, but we have seen that the lattice, if the lattice changes, then the critical parameter may change. Okay. So we have shown that in any dimension, the critical parameter for elephant random walk, the PD depends on the dimension and depends on lattice. But the step reinforcement works has a uniform critical parameter in dimension 1 and 2. But indeed, it's also true in higher dimensions in terms of escape rate. We have mentioned that in dimension at least 3, the step reinforcement work is transient. Then we want to estimate the escape rate. So under the assumption A2 plus delta, we can show that essentially this proposition shows that the norm Sn grows like into the 1/2 if alpha is less than 1/2, and it goes like into the alpha if alpha is greater than or equals to 1/2. So there is still a phase transition at 1/2. It's some phases may call it first order phase transition because the derivative has a phase transition. Okay, so let me summarize the results on recurrence and transience. We have shown that under the 2 plus delta moment assumption, in dimension 1 and dimension 2, there is a phase transition between recurrence and transience. And in higher dimension, there is still a phase transition in terms of escape rate. Okay. Any questions so far?
It is okay.
Yes. So just now we talked about recurrence and sorry, any question? Yeah. So just now we talked about recurrence and transience and escape rate. They are all properties of the radial component if we use the polar coordinates. How about the angular components? Indeed, there is also a phase transition at alpha equals 1/2 for the angular components. We can show that there's a limiting direction if and only if alpha is greater than 1/2. So under the second moment assumption, if alpha is greater than 1/2, then Sn divided by its law, basically it's this will be a unit vector if Sn is not the zero vector. If alpha greater than 1/2, this limit exists. But if alpha less than 1/2, this limit does not exist almost surely. Okay, maybe it would be better. It would be better to look at this simulation results. I plot 4 independent two-dimensional elephant random walks, each with 1 linear steps. So the left figure shows the case when alpha equals 0.33, when essentially it says when alpha is less than 1/2. The simulation result is somehow similar to simple random walks. There is low limit direction. But when alpha is greater than 1/2, somehow we are stretching this the sample path become more straight. In this case, the elephant network, or in general, a steep reinforcement network, has a limiting direction. Okay. Okay. Any question before I review some previous results on steep reinforcement work?
I think.
Okay.
Yes, please.
Yes,
Here,
Dr. Alistar. Yes.
considering the recurrence, is it positive or null? Here.
Well, it's still unknown. For elephant random work, for elephant random work in dimension one is known. That's the it's positive recurrent if and only if so it was solved by Botwa and his students Fang Zhen, I think. In dimension one for elephant random work is positive recurrent if and only if p is less than 1/6 1/6. But for if I if I'm right. But for general stable reinforcement work or in higher dimension, I think it's still unknown whether it's positive recurrent or non recurrent.
Okay, thank you.
Yes. Okay, let me quickly review some previous results. For stable reinforcement work, for alpha less than or equals to 1/2, okay, in dimension one, it has the invariance, the weak invariance principle and the strong invariance principle have been established. So essentially, essentially Botwa shows that when alpha is less than 1/2, in the sense of square root, the normalized stable reinforcement work converts to the so-called lowest reinforced Brownian motion. Yeah. If you look at the drift terms, there's a alpha times b hat divided by t. It somehow corresponds to the discrete case when for the conditional expectation of the next step. If you compute the conditional expectation of x plus x n plus 1, you get Sn times alpha divided by n. So, but at least this stochastic differential equation for audience who are interested in SD, but I'm not working on this direction. So anyway, and Hu and Zhang established the strong invariance principle, so from which one can deduce the law of the iteration logarithm. It says that if the second moment exists, then Sn grows at most the square root of n times log n. It's just like a simple random walk or the classical random walks. And this law, the large number law was also established for any alpha. If the first moment exists, then Sn divided by n will convert to the expectation of the expectation of mu, almost surely. And when alpha is greater than 1/2, this model shows a very different behavior from the so-called diffusive region and the critical region. So essentially, when alpha is greater than 1/2, we have almost sure convergence. So Sn divided by Sn minus n times the expectation divided by n to the alpha will converge to some random vector, almost surely, and in L2. So we have shown that we have seen that for alpha less than or equal to 1/2, Sn the normalized Sn converts to converts to converts in expectation. Sorry, converts in distribution. Basically, converts in distribution to the normal distribution, and we have an invariance principle. But if for alpha greater than 1/2, Sn itself has certain kind of almost sure convergence result. And yeah, so before I mention the working with Zigmark type strong law of large numbers, I would like to mention that I just noticed that Professor how to say Rafik recently proved a similar result, probably even a stronger version. But I also have a similar result, even though I haven't published. But essentially, it's covered in the first version of my paper, recurrence and transience of state reinforcement work. So we have shown that we have seen that for state reinforcement work, we have a strong law of large numbers. We also we are curious about the convergence rate. If the second moment exists, then we can use the law of iterated localism. But if the S moments exist for some S between 1 and 2, we also have certain kind of estimate for the strong law of large numbers. Okay, this somehow is used in our proof for the recurrence and transience.
May I ask a question, please? In
Yes.
point 2, you have the almost sure convergence for the limit theorem.
Yes.
That's funny because in dimension
So
1,
yes, good question. In dimension sorry to interrupt you. For alpha greater than 1/2, we have a almost sure convergence. So essentially, to show that in this case, to show that it's transient, it's suffices to show that the random vector is not a zero vector. Yeah. So sorry to interrupt you. Can you continue your question?
because in dimension 1, most of the time the authors cover convergence in distribution, right? And here you are in
No, for alpha less than less than or
a superior critical case, alpha bigger than 1/2.
bigger than 1/2. Yes.
Yes. In dimension 1, most of the time, at the best of my knowledge, the others recover only convergence in distribution. And here, you say that Bertrand in 21 has an almost sure convergence. Okay, I'll check. Thank you.
So indeed, Bourtois in his paper he proved the L2 convergence result. Indeed. Then Bartin proved the almost sure convergence result.
Okay, thank you.
Yeah. Maybe you can check. Yeah.
Yeah.
Okay.
Thank you.
Any question before I talk a little bit on this proof strategy? Yeah, before my time is limited, so I probably will skip some details. So I will only talk about this the proof for the subcritical region for alpha less than 1/2. So the basic idea is to use the Lyapunov function method. And to use this method, we have to control the past. Indeed. So this is somehow philosophy. We have to control for the reinforcement works. Sometimes we have to control the past so that we can control the future. Yes. So the Lyapunov function method was developed by Lamberti into 1960. The basic argument is as follows. So imagine that we have a Markov chain, irreducible Markov chain on ZD, and we have a function f, which we call Lyapunov function, such that f goes to infinity as x goes to infinity. And it satisfies and the conditional increments of f is negative if xn is outside of large ball. Then we can use martingale argument to show that xn will return to this fixed ball infinite many times, almost surely. So the argument is that like this. So we let tau be we assume that xk is not inside this ball, and tau be the first time it returns to this ball. Then by our assumption, f of xn, which tau is a lower bounded, is a lower bounded supermartingale, and thus converge almost surely. But if tau, on the event that tau equals infinity, xn will goes to infinity. So f will goes to infinity. So this occurs with probability 0. So this shows that each time you exit from this fixed ball, you return almost surely. So this shows that we will return to the fixed ball infinite many times. Okay. So for example, in dimension 2, we can use we can take f to be the square root of log x. Yeah. Okay. But for our case, we can imagine that this elephant random walk is like a random walk in a dynamical environment. So, but the environment is dynamical because the environment is affected by the past, by the trajectory, or by the past of this work. So we can compute, by definition, we compute. So at time n, we compute the transition probability for the next step. It's given by alpha times n divided by n plus 1 minus alpha divided by 4 for each direction. So then we can simply assign weights to the corresponding edges. So if we rewrite this weight, it equals 1/4 plus alpha times the difference between the empirical measure of steps of the step sequence and the uniform distribution on the 4 directions. So the basic idea is to show that the second term, n divided by n minus 1/4 converts to 0. So the second term is very small, so that in your long term, this elephant random walk just simple for alpha is less than 1/2, behave like a simple random walk. So then we can use some techniques for simple random walk or for classical random walks. So by using stochastic approximation results or some well-known results for finite color polyarms, one could prove that. So let me remind you that n of v is the number of steps S has made to the direction v up to time n. So then you can imagine that this is the empirical distribution of the step sequence. Okay, so this lemma shows that this empirical distribution will converge to the uniform distribution on the 4 directions. At the rate, roughly speaking, at the rate 1 over the square root of n. Then we can define a stopping time tk. So for some, then for large k, before time tk, this elephant random walk behaves very like simple random walk. And we know that for sufficient large k, tk is infinity by this level. Okay, so this is essentially this is the basic idea for our proof. So I think my time has run out, right?
We have 5 minutes. 5 minutes.
Yes. Yeah. Oh, okay. Let me quickly. Okay. So now we need to first prove Wicker results, which show that the growth rate of this elephant work in dimension 2, when alpha is less than 1/2, is somehow less than n to the s, where s is a constant less than 1/2. The proof is as follows. We assume that sk is greater than k to the s, and we define tau k be the first time it's catched up by this growing ball into the s. And we use the same Yapu function as the classical case. We let f be the square root of log x. Then by using Taylor expansion, one can show that before time tk, we have this inequality. We have some estimate on the conditional increments. And for the term alpha divided by 2n times the square root of log Sn, the summation of this term is bounded by the square root of s times log n. So that shows that the summation of the second terms is somehow goes is upper bounded by the square root of s times log n. Then we have a lower bounded super martingale m, so that it converges almost surely. Then this shows that f of Sn is somehow upper bounded by the square root of s times log n. So then Sn is upper bounded by n to the s. The rigorous arguments is like this. We have shown that Mn is converges almost surely, but using the law of iterative logarithm, we know that the limit soup of Sn is somehow like the square root of n. But we have chosen s. We have chosen s such that s is less than 1/2. So on this event, that both tau k is the time that it returns to the growing ball and with radius into the s. Tk is the stopping time that before tk it behaves like a simple random walk. This shows that either tk is finite or capital sorry, tau k is finite or capital tk is finite. But we know that for large k, capital K tk is infinite. So this shows that for large k, tau k is finite. But this also shows that for any k, indeed for any k, tau k is finite. So this is the argument for the weaker result. So this two-dimensional elephant work will return to the growing ball of radius n to the s infinitely many times. Then this guarantees that we can start our elephant work with a very good initial conditions, which matters for reinforced processes. We can assume that this process start with s with the location such as s nk is upper bounded by nk to the s, and the empirical distribution is very close to the uniform distribution. Then using a similar argument, we can show that in this case the function f itself, okay, itself is a non-negative super martingale before time theta k. theta k is the time that S is exit from a larger ball of radius into the T. T is a constant greater than S, but still less than 1/2. Then we can use optimal stopping theory to show that for this elephant run work, if it wants to reach the boundary of into the T before it returns to some fixed ball, it has to pay a price. That is, this probability, this condition probability, is bounded away from 1. Then by using the V01 law, we can show that the either tau k is finite or capital TK is finite. But we know that for large K, capital TK is infinite. So this shows that this work will tau k is finite. This work will return to the fixed ball of radius r infinite many times. This proves the recurrence. Sorry for I just quickly review the proof. Okay, let me summary our main results. So firstly, for the radial components, in any dimension, we show that at alpha equals 1/2, there is a phase transition. In dimension 1 and dimension 2, there is a phase transition between recurrence and transience. And in higher dimension, there is a phase transition between the escape rate. Okay, and we also prove the angular components. We also prove the phase transition for the angular components. Well, alpha is greater than 1/2, there is a limiting direction, almost surely. And for alpha less than or equal to 1/2, there is no limiting direction. Okay, this is all about today's talk. Thank you very much.
Thank you for you, Dr. Shuo. Some questions, please.
Yes, please. I have one question.
Yes, Dr.
Yes.
Abdestar. Yes, please.
Thank you. Thank you very much for the talk. You have mentioned in the proof that you use the Lyapunov function, which is
Yes.
for Markov chains. Is the
Yes,
elephant work in the
because for
two-dimensional
Markov,
case? Is it Markovian to use the Lyapunov function here, your process?
no. So can you see my screen? So for the display 5.1, for the Markovian case, the left-hand side is a function of xn, right?
Mhm.
And for the two-dimensional elephant work, it actually is non-Markovian. So the left-hand side depends on the past. It's not just a function of xn. But it's a function of it's a function of xn and the empirical distribution. If you the empirical distribution, I mean this n of v divided by n. So it counts how many steps this elephant has made to each direction v. So how to say? So for elephant run work, it's non-Markovian. But if we allow it to move with his memory, it becomes a Markovian. Essentially, in dimension 2, it has like a 4-dimensional memory. So Sn itself is non-Markovian, but Sn and the empirical distribution, the 4-dimensional vector, this joint process is Markovian. So for 2-dimensional elephant work, the left-hand side. Hello.
Okay.
Yeah, for the two-dimensional case, for the two-dimensional elephant work, left-hand side depends on Sn and the vector n of v. We are going to using approximation result to replace this empirical distribution by the uniform distribution, so that essentially it will depend only on the current position. Okay.
Star, you have other questions?
Yes, I have a question.
Yes, Dr. Mohammed. Yes.
Thank you very much, Dr. Shuo Qin, for this nice talk. I would like to ask you about the definition of your model. If I understand, it's a multidimensional version of the so-called positively reinforced random walk, like in the Simon algorithm, right?
Yes, 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 yes.
Okay, I would like to ask you, what about the unbalanced version of this Simon's algorithm introduced by Jean Bertoin? Do you, it's possible to define a multidimensional version of this unbalanced random walk? And I am wondering if it's possible to do the same things, the same approach in this case.
So, hi, Rafik. I remember you recently published the paper on unbalanced reinforcement work, right?
Yes.
Uh, uh, so I didn't check, but I think so. My feeling is that uh, for alpha less than one half. Sorry, I didn't check the precise definition of unbalanced stable reinforcement work.
Okay.
But my feeling is that when alpha is less than one half, the stochastic approximation or the approximation result is still true. This is my feeling. Yeah,
Mm.
I haven't checked, so that you can
Okay.
still approximate this stable, the balanced or either balanced or unbalanced stable reinforcement work by the classical random works.
Okay. Okay.
For alpha,
Y-
for alpha is large enough, it may not be true. Yes.
mm, mm. Okay. Okay. Thank you. Thank you.
Other questions, please? Just I have a remark on the slide 9, please. About the result, slide 9.
Sorry. This is yes.
9, okay.
This or
I think 9, but I have forget what is the remark. 9, not 10. 9.
9.
9, yes. Okay.
Yes.
Okay, here is the point 2. You mean the limit sup or limit inf of Sn less than R equal 1?
Limit inf. Yeah,
Limit.
but for limit soup it's impossible because we already have some like the law of iterated logarithm, which shows that the limit soup
Okay.
is like grows like square root of n times log n. Yeah.
Okay. Slide 12, please. Okay. Can you give an idea the origin of the 7/12? Why we have a phase transition in P equals to 7/12? Just a large idea.
Yeah. Uh so uh so here we rewrite the elephant random walk as a step reinforcement walk, right? Just above the second formulation,
Okay.
right? So here you indeed with if you replace this 2D minus 1 by 5,
Mm-hmm.
if you replace 2D minus 1 by 5, this just gives just how to say you transfer the elephant random walk on the triangular lattice to the two-dimensional step reinforcement walk. So in this case, alpha equals, so here you can simply let d equals 3. Here alpha p equals 6p minus 1 divided by 5. So now we can transfer the elephant random walk on triangular lattice to two-dimensional step reinforcement walks. So here alpha equals 6p minus 1 divided by 5. So locally, it's the elephant random walk on triangular lattice behave like a elephant random walk on Z3. It has 6 directions to choose.
Okay.
So in this, then let's explain why we can get p equals 5 alpha plus 1 divided by 6. So we have shown that when alpha equals 1/2, there is a phase transition. We simply insert alpha equals 1/2. Then we get
Okay.
p equals 7/12. Yes.
Okay. Thank you. Okay. Other questions, please?
Yeah, yes, Rafik. Maybe just yes, a question about the role of the lattice in what you have done. I'm not sure to understand if it depends on the lattice or not. It's a very okay.
Sorry, what's your question?
My question is, yeah, you told us that it's possible to consider the lattice ZD, Z to the power D, but you can consider more.
Yes, like triangular lattice. Yes.
Yes. So the definition of the lattice is given by 3.1. Is this? I'm not sure.
This is the definition of lattice. For elephant random walk on lattice, we simply replace the how to say, you can use the same definition. So but the only difference is that in like in ZD,
Yeah.
we either choose repeat the remember with parameter p, we repeat this remembered step. Otherwise, we choose one of the 2D minus 1 remaining directions, right?
Yes.
But for different lattice, like for triangular lattice, for example, even though
Okay.
it's in dimension 2, we have 5 remaining directions because there are in 6 directions in total, right?
Okay. So in fact, the main difference is the number of direction for the step of the elephant. No?
Yes, but actually, so the how to say, the number of directions does not really matter. The matter, how to say, the number of linearly independent vectors matters. For Z2 or like planar triangular lattice, they only have 2 linear independent vectors. Like say in
Okay.
Z2
Okay.
it's E1 and E2, and
Okay.
for the triangular lattice, even though we have 6 directions, but actually um we have 2 linear independent vectors, so it's still in dimension 2.
Okay. 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 I understand.
So
Thank you
that's
very much.
explain why in dimension 3 it's transient. We have 6 choices for 6 directions, but in dimension 2 it still has 6 choices, but it's recurrent because
Yeah.
this is a number of linear independent vectors.
Okay. Thank you. Thank you very much.
Other questions, please? Okay, if no other questions, we have to thank again Dr. Shuo for this nice talk, and see you next week for another talk. Thank you again, Doctor. Thank you.
Thank you very much.